Today, Antarctica is a place that defies life. It is the coldest region on Earth, where temperatures fall far below anything humans can survive without technology. Winds sweep across the ice faster than hurricanes, carrying snow that never melts. Moisture barely exists, making the continent technically a desert. From space, it appears as a smooth white shield at the bottom of the planet, reflecting sunlight back into space like a mirror. It looks permanent, ancient, and unchanging, as if it has always been frozen. Yet this image is deeply misleading. Beneath nearly 3 kilometers of ice lies a different world. Not a metaphorical world, but a literal one. Forest soil, river sediments, pollen grains, even the remains of animals. These discoveries were not found in theory or speculation. They were recovered by drills pushed through the ice and by rock exposures along the coast where glaciers have scraped the land clean. Every layer scientists uncovered carried the same message: Antarctica was once alive. To understand why this is shocking, one must consider the continent's present position. Antarctica sits directly on the South Pole. For half the year, it receives constant sunlight, and for the other half, it receives none at all. During winter, darkness covers the land for months without interruption. No sunrise, no twilight, only starlight, and the glow of the aurora. Even during summer, the sun never rises high in the sky. It circles low along the horizon, providing weak energy compared to equatorial regions. In such conditions, complex ecosystems should be impossible. Trees cannot grow without regular sunlight cycles. Large animals cannot survive extreme seasonal starvation. Rivers should remain frozen year-round. And yet, geological evidence proves all of these things existed there. The contradiction begins with continental drift. Earth's crust is not static. It is divided into tectonic plates that slowly move across the mantle over millions of years. The continents have never stayed fixed in their current arrangement. Long before humans existed, long before mammals even dominated the land, Antarctica was not isolated at the pole. It was part of a massive southern supercontinent known as Gondwana. Gondwana joined together what are now South America, Africa, India, Australia, and Antarctica into one continuous landmass. Instead of surrounding the pole, this continent stretched across warmer latitudes. Antarctica was positioned much farther north than today, closer to temperate climate zones. The pole itself lay somewhere else entirely. The world map would have looked unrecognizable. Because of this placement, Antarctica received far more solar energy than it does today. Seasonal darkness still occurred, but temperatures were dramatically higher. Oceans circulated warm water across the region. Rain fell, rivers flowed, soil formed. In every ecological sense, Antarctica functioned as a normal continent. The proof lies in its rocks. In exposed mountain ranges such as the Transantarctic Mountains, layers of sedimentary rock contain compressed plant material that has transformed into coal. Coal forms only when enormous amounts of vegetation accumulate in wet environments and are buried over long periods. It requires dense plant life, stable water systems, and relatively mild climates. A frozen wasteland cannot produce coal. Yet, Antarctica contains vast coal deposits. When geologists first reported these findings in the early 20th century, the conclusion seemed impossible. A land buried under endless ice once supported forests large enough to leave behind industrial-scale carbon deposits. At the time, continental drift was still controversial, and many scientists struggled to explain the evidence. Only later, when plate tectonics became widely accepted, did the puzzle resolve itself. The continent had moved. Movement, however, explains only location, not life. Even in warmer latitudes, Antarctica would still experience unusual light cycles because of its southern position. Months of darkness would challenge any ecosystem. Plants require photosynthesis. Animals require plants. Survival demands adaptation. Fossilized tree trunks discovered along Antarctic coasts revealed those adaptations. The growth rings within the wood differ from trees in tropical regions. Instead of continuous growth, they show strong seasonal variation, indicating rapid summer expansion and winter dormancy. These were not jungle trees, but polar forests, capable of enduring long periods without sunlight. They stored energy during bright seasons and shut down metabolic activity during darkness. Such forests would have appeared strange compared to modern ones. During summer, they would burst into intense productivity, leaves absorbing sunlight almost continuously as the sun circled the sky. During winter, they would stand silent and leafless for months, waiting for the sun to return. The ecosystem pulsed annually rather than maintaining constant activity. Animal life adapted alongside them. Though few large fossils were initially known, microscopic remains told a clear story. Spores, pollen, and freshwater microorganisms found in sediment layers confirmed stable lakes and wetlands existed. These were not temporary thaw periods, but long-lasting environments. The continent supported complex biological cycles over immense spans of time. The existence of these ecosystems forces a reconsideration of Antarctica's identity. It is not inherently a frozen continent. Ice is only its current state, not its defining feature. The land beneath the ice is older than the ice itself and remembers a completely different climate. As researchers drilled deeper into the ice sheet in the late 20th century, they expected only frozen water and ancient air bubbles. Instead, some cores contained traces of organic material carried upward by moving glaciers. Tiny fragments of plant matter, preserved by cold and pressure, appeared where none should exist. Each fragment reinforced the same conclusion. Antarctica did not freeze instantly. It transitioned from a living landscape into the polar desert seen today. The question then becomes not whether Antarctica was warm, but how such a transformation occurred. A continent does not simply cool overnight. The process required global changes affecting oceans, atmosphere, and planetary circulation. Antarctica's story is therefore not only its own history, but part of Earth's climate evolution. Before the ice, before isolation, Antarctica participated in a shared world ecosystem. Animals migrated across Gondwana without crossing oceans. Plants spread across connected forests from what is now South America to what is now Australia. The southern hemisphere functioned as a unified biological network. Standing today at the South Pole, surrounded by silence and endless white, it is difficult to imagine that this same ground once held flowing rivers and rustling leaves. Yet the rocks confirm it. Antarctica should not exist as we know it, because its present condition is temporary in geological terms. It is the result of motion, timing, and climate mechanisms acting together over tens of millions of years. The frozen desert is only the final chapter of a much longer narrative, one that began in warmth. If Antarctica was once warm, the transformation into ice must have had a beginning. The change did not start with snowfall or glaciers. It began with motion so slow no creature living at the time could perceive it. The continent itself was traveling. Tectonic plates move at a pace measured in centimeters per year, about as fast as fingernails grow. Over a human lifetime, the distance is insignificant, but over tens of millions of years, continents cross entire climate zones. Gondwana, the southern supercontinent, did not remain intact. Internal stresses built within Earth's crust as heat circulated through the mantle below. Eventually, fractures formed, and the landmass began to split. At first, the changes were subtle. Large rift valleys opened between what would become Africa and South America. Farther east, India began to separate and drift north toward Asia. Australia pulled away gradually. Antarctica, still connected along broad edges, started losing its neighbors. Each separation altered ocean circulation patterns. Water could now flow into spaces that had once been blocked by land. Climate on Earth depends heavily on how oceans move heat around the globe. Warm water leaving equatorial regions carries energy toward the poles, moderating temperatures. When continents obstruct or redirect currents, entire regions can warm or cool without any change in sunlight. Antarctica's cooling would eventually come from this mechanism rather than a decrease in solar radiation. As South America and Australia drifted away, Antarctica became increasingly isolated. Shallow seas expanded between the continents. These waters did not freeze immediately. Instead, they allowed currents to begin circulating around the southern landmass. At first, warm currents still reached its coasts, maintaining forests and wetlands. But circulation patterns were changing in ways no living organism could adapt to quickly. Sediment layers from this transitional period reveal a gradual environmental shift. Plant fossils become less diverse upward through the rock record. Thick forest indicators thin out. Instead of broad leaves typical of warm conditions, later layers contain more cold-tolerant species. Growth rings in fossil wood become narrower, suggesting shorter growing seasons. The continent was cooling slowly, generation by generation. Animals faced similar pressure. Large amphibians and reptiles that required stable warmth disappeared first. Smaller, more adaptable species persisted longer. Burrowing behavior increased among vertebrates, inferred from fossilized tunnel structures preserved in ancient soils. Creatures sought insulation underground during harsher winters. Survival no longer depended only on food availability, but also on enduring cold darkness. The cooling climate affected water systems as well. Rivers that once flowed year-round began freezing seasonally. Lake sediments show alternating bands of biological productivity and dormancy, evidence of ice cover forming part of each year. Yet, even during this period, Antarctica remained far from its present state. Summer temperatures still rose above freezing, and forests still covered much of the land. Meanwhile, the atmosphere responded to geological change. As mountain ranges formed along separating plate boundaries, wind patterns shifted. Increased weathering of newly uplifted rocks removed carbon dioxide from the air through chemical reactions with rainwater. Lower greenhouse gas concentrations reduced global heat retention. This was not an isolated Antarctic event, but a planetary cooling trend, with Antarctica experiencing amplified effects due to its southern position. The decisive turning point approached as the final land connections narrowed. Between Antarctica and South America lay a shallow barrier that limited full ocean circulation. Between Antarctica and Australia, another partial connection remained. For millions of years, these barriers slowed the exchange of water, allowing some warm currents to still reach the continent. Forest ecosystems, though stressed, endured. Geologists can trace the exact timing of separation through magnetic signatures in seafloor rock. As molten material rises at spreading ridges and cools, it records the direction of Earth's magnetic field at that moment. By mapping symmetrical magnetic stripes on opposite sides of ocean ridges, scientists reconstructed when ocean basins opened. These measurements show that by roughly 35 million years ago, Antarctica became completely surrounded by open ocean. This isolation triggered the formation of a powerful current encircling the continent. Unlike other ocean currents that bend north or south, this one flowed continuously around the globe without hitting land. It prevented warm equatorial water from reaching Antarctic shores. Instead, cold water spun endlessly around the continent like a barrier. Temperatures fell sharply compared to previous millions of years. Snow that once melted each summer began surviving through the next winter in some regions. Permanent ice patches formed in mountain valleys. Glaciers started to grow, not from massive snowfall, but from accumulated seasons where melting could no longer keep pace with freezing. Evidence of the first glaciers appears in rocks containing scratched surfaces known as glacial striations. Stones embedded in moving ice carved parallel lines into bedrock, leaving unmistakable marks. Nearby sediments contain dropstones, rocks carried by icebergs and released into marine mud when the ice melted. These features confirm the birth of Antarctic ice sheets. The shift was not instantaneous. For long intervals, ice advanced and retreated. Warmer cycles temporarily reduced glaciers, allowing vegetation to reclaim ground. But each cycle favored cold conditions slightly more than before. Over time, ice coverage expanded further after every retreat. Eventually, a threshold was crossed. The reflective surface of growing ice increased the planet's albedo, meaning more sunlight bounced back into space. This feedback amplified cooling. Larger ice sheets produced colder air, which produced more ice. Antarctica was no longer merely cooling, it was entering a self-sustaining frozen state. The forests that had survived for hundreds of millions of years vanished, not because a single catastrophe destroyed them, but because no season remained long enough for regrowth. Soil froze. Roots could not penetrate permafrost. Rivers locked into ice channels. Life retreated to the surrounding oceans where water retained heat more effectively than land. By the time permanent continental ice formed, Antarctica had transformed beyond recognition. The land that once participated in Gondwana's shared ecosystem became an isolated polar mass. Its climate no longer resembled any other place on Earth. What stands today as a vast white desert is the accumulated result of slow separation, altered currents, atmospheric change, and feedback loops acting over immense time. The continent did not suddenly freeze. It was gradually abandoned by warmth. Long before the first glacier appeared, Antarctica was not a land of silence. It was a land of sound. Wind moved through branches instead of across empty ice. Water flowed through channels instead of remaining locked beneath frozen sheets. The ground was dark with soil, not buried under kilometers of compressed snow. To imagine this earlier Antarctica requires abandoning every modern visual reference. The continent was still polar, but it was alive. Roughly 260 to 250 million years ago, during the late Permian period, Antarctica lay farther north than today, but still within high southern latitudes. The sun's path across the sky behaved much as it does now near the pole. For months the horizon glowed continuously, the sun circling without setting. Then for months it vanished entirely. This extreme seasonal cycle shaped everything that lived there. The vegetation was dominated by plants, unlike modern flowering species. Grasses had not yet evolved. Instead, enormous fern-like plants and primitive seed-bearing trees covered the land. Among the most common were glossopteris forests, tall woody plants with broad tongue-shaped leaves. Their fossils are found across what were once parts of Gondwana, linking Antarctica to South America, Africa, India, and Australia. The distribution of these plants became one of the earliest clues that the continents had once been joined. These forests thrived in wet soil. Rivers meandered slowly across broad plains, overflowing during seasonal melts and feeding swampy lowlands. Thick layers of fallen leaves accumulated in standing water, protected from decay by low oxygen conditions. Over time, these deposits compressed into peat and eventually coal. The presence of coal seams within Antarctic rock proves the land supported vast quantities of vegetation for long periods. Despite the long winter darkness, plants adapted effectively. During the continuous daylight of summer, photosynthesis occurred nearly 24 hours a day. Growth rates surged, storing large amounts of energy within roots and trunks. When darkness arrived, metabolic processes slowed dramatically. Leaves fell and the plants entered dormancy. Instead of dying each winter, they endured it in a suspended state until sunlight returned. The climate itself was milder than modern polar regions, but still cool compared to tropical environments. Average temperatures may have hovered near freezing in winter and risen comfortably above it in summer. Snow likely fell, but seasonal melting prevented permanent ice accumulation. The atmosphere contained higher concentrations of carbon dioxide than today, trapping heat and moderating extremes. This greenhouse effect allowed ecosystems to function despite latitude. Animal life populated these forests. Early reptiles, amphibians, and insect species occupied freshwater systems and undergrowth. Though many fossils are fragmentary, footprints preserved in ancient soils reveal active terrestrial communities. Some animals were small and agile, capable of hiding within burrows to escape cold periods. Others depended on aquatic habitats that remained partially unfrozen beneath insulating layers of surface ice. Insects played a major ecological role. Fossilized wings and exoskeleton fragments show diverse forms adapted to seasonal abundance. During summer, they would have emerged in massive numbers, feeding on plant material and each other. During winter, many species likely survived as eggs or larvae beneath soil and leaf litter, waiting for warmth. The forests themselves were not uniform. Higher ground supported taller trees with deep root systems, while lowland basins formed marshes dense with spore-producing plants. Mosses and smaller ferns carpeted shaded regions near water. The constant summer sunlight allowed extended periods of growth, making the landscape intensely green for half the year. Rivers carried sediment from distant mountains across floodplains. Seasonal flooding redistributed nutrients, renewing the soil annually. These conditions created stability across millions of years, long enough for thick ecological networks to develop. Predator and prey relationships balanced, and plant communities spread across thousands of kilometers of connected terrain within Gondwana. One remarkable feature of polar forests was the low angle of sunlight. Even at noon, the sun remained close to the horizon. Shadows stretched long across the ground, and light penetrated sideways through branches rather than from directly overhead. Plants evolved leaf structures optimized to capture this shallow illumination. Broad, flat leaves maximized surface area, allowing efficient energy absorption. During winter darkness, the environment transformed. Temperatures dropped, rivers froze at the surface, and animal activity decreased sharply. But unlike modern Antarctica, the freeze was not absolute. Subsurface water continued to flow, and buried plant roots remained viable. The ecosystem entered a prolonged pause rather than extinction. When spring returned, thaw occurred rapidly. Snow melted, streams overflowed, and dormant life resumed activity. This cycle repeated for millions of years. Entire generations of organisms lived and died under these rhythms without any sign that the continent would one day become uninhabitable. Geological stability allowed evolutionary specialization. Species did not prepare for permanent cold because it did not yet exist. Sedimentary rock layers record these cycles clearly. Alternating bands of organic rich material and mineral deposits show repeated seasonal growth and dormancy. Tree ring patterns confirm annual changes in productivity. Fossil pollen concentrations spike in certain layers, indicating seasonal release events. Each piece of evidence contributes to a coherent image. Antarctica functioned as a polar forest biome. At this time, the continent was not isolated. Animals could migrate across land bridges connecting distant regions of Gondwana. A creature moving far enough north would encounter warmer climates without crossing oceans. This connectivity supported genetic diversity and prevented ecological collapse during local environmental stress. Yet beneath this thriving world, forces were already shaping its future. Tectonic stresses were slowly rearranging the supercontinent. Volcanoes erupted in distant regions. Atmospheric composition fluctuated due to large-scale biological and geological processes. None of these changes immediately threatened the forests, but they formed the background conditions that would later alter global climate. For the organisms living there, Antarctica was simply home. Dense vegetation, flowing water, and seasonal light-defined existence. The concept of a frozen continent did not yet exist in Earth's history. That transformation belonged to a future millions of years away, beyond the lifetime of every species inhabiting the forests. The land at the bottom of the world once held a complete ecosystem, shaped by darkness but sustained by warmth. The polar forests of ancient Antarctica were not fragile ecosystems barely surviving the cold. They were stable, long-lasting environments that endured for tens of millions of years. Stability in nature does not come from gentle conditions, but from balance. Every organism filled a role, and each seasonal cycle reinforced the structure of life across the continent. During the long summer, sunlight never disappeared. Instead of rising and setting, it moved in a circle around the sky. The angle changed slowly, but darkness never came. For plants, this meant continuous photosynthesis. Energy production did not stop each night, as it does in most regions of Earth. Growth became concentrated into a single intense season. Trees expanded rapidly, pushing out leaves, branches, and reproductive structures in a short window of favorable conditions. This growth produced enormous amounts of organic material. Leaves fell into rivers and marshes, building thick layers of plant debris. Microorganisms consumed some of it, but much remained buried in waterlogged soil. Oxygen levels beneath the surface stayed low, preventing full decomposition. Over time, these deposits compressed under sediment and transformed chemically into carbon-rich layers. Millions of years later, these layers would be discovered as coal, silent testimony to forests no one would ever see again. Animals synchronized their behavior with the same cycle. Herbivores fed continuously during the bright season, building fat reserves to survive winter scarcity. Carnivores followed their prey, hunting during the months of abundance and enduring periods of near inactivity later. Fossil trackways preserved in ancient mud show migration patterns along riverbanks and across floodplains. The land was not static. It was crossed by moving populations, responding to light and temperature. Winter changed the landscape dramatically. the sun vanished entirely below the horizon, plunging the continent into darkness lasting several months. Temperatures dropped below freezing across wide regions, and surface water solidified. Yet life did not disappear. Instead, it slowed. Burrows became essential shelters. Many vertebrates likely survived underground, where soil insulated against extreme cold. Fossilized tunnels found in Antarctic rock indicate repeated occupation, not temporary refuge. Animals return to the same protected spaces year after year, forming seasonal habitats much like dens used by modern mammals in cold climates. Plant life relied on dormancy. Leaves shed before darkness to reduce energy consumption and prevent damage from freezing. Stored nutrients in roots and trunks maintained basic cellular function. When sunlight returned, growth resumed from preserved tissue rather than from seeds alone. This adaptation allowed entire forests to recover quickly each year without re-establishing from scratch. Freshwater systems also persisted beneath ice cover. Even when lakes froze on the surface, water remained liquid below. Sediment cores show uninterrupted microbial activity through winter layers, meaning ecosystems continued at reduced levels. These aquatic environments acted as refuges for small organisms and possibly for amphibious animals capable of remaining submerged for extended periods. The atmosphere during this time supported such resilience. Carbon dioxide concentrations were significantly higher than modern levels, strengthening the greenhouse effect. Heat retention reduced the severity of winter lows and ensured complete freezing never penetrated deeply into the ground. Antarctica was cold, but it was not lethal. One of the most important characteristics of this forest world was its connectivity. Gondwana still existed as a unified landmass. A species living in Antarctica could gradually expand its range northward across continuous terrain into milder climates. This movement prevented isolation and allowed recolonization after local disturbances. The continent did not stand alone. It functioned as the southern extension of a vast ecosystem. Geological evidence shows similar plant species across distant southern continents, proving this connection. The same Glossopteris leaves appear in rock formations thousands of kilometers apart today. Their identical structures confirm they grew within a shared environment before the land separated. Antarctica was not peripheral but central to a global ecological network. However, subtle signs of change began appearing late in this period. Sediment layers reveal increasing variation in temperature indicators. Some years produce thicker growth rings, others thinner. The differences were small but persistent, suggesting a climate gradually becoming less predictable. Volcanic activity elsewhere in Gondwana released gases and ash into the atmosphere, occasionally altering sunlight penetration and temperature patterns. Over many generations, certain species adapted to slightly cooler conditions. Others disappeared from higher latitudes while continuing farther north. The forests did not collapse, but their composition shifted. Diversity slowly decreased in the southernmost regions. These were early warnings of a future transformation. Though no organism could perceive it, beyond immediate survival. Time scales in geology dwarf biological awareness. For animals and plants living there, each year resembled the last. Even over thousands of years, the environment appeared stable. Yet over millions, small trends accumulate into irreversible change. The position of the continent continued drifting southward. Ocean gateways widened incrementally. Heat distribution across the planet altered step by step. By the end of this era, Antarctica still held forests, rivers, and animal communities, but the margin of safety had narrowed. Winters lasted slightly longer. Summers were marginally cooler. Snow persisted a bit farther into the warm season than before. These differences were subtle enough to be nearly invisible in a single lifetime, but powerful enough to shape evolution. The lost forest world was not destroyed suddenly. It faded slowly, like a season extending beyond its natural end. The balance that sustained it for millions of years was beginning to shift, setting the stage for entirely different inhabitants in the ages to come. By the time the Permian forests had endured their long age of stability, life on Earth faced one of the greatest disruptions in its history. A mass extinction at the end of the Permian eliminated the majority of species across land and sea. Entire ecological systems vanished. When life recovered in the following Triassic and Jurassic periods, the creatures that rose to dominance were unlike those before. Among them were the dinosaurs. Antarctica did not escape this global transformation. The ancient forests changed composition, and new species spread across Gondwana. The continent still lay connected to other southern lands, allowing animals to migrate freely. Over time, dinosaurs reached the high southern latitudes and established permanent populations. They were not temporary visitors. Fossils show they lived and reproduced there year-round. This idea once seemed impossible. For decades, dinosaurs were imagined as creatures of hot swamps and tropical jungles. Popular reconstructions placed them beneath blazing suns among dense ferns in equatorial regions. The discovery of their remains in Antarctica challenged that image completely. A land already known for seasonal darkness and cold hosted large reptiles once believed dependent on warmth. One of the most famous Antarctic dinosaurs is Cryolophosaurus. Its name means cold-crested lizard, taken from the distinctive ridge across its skull. The fossil remains were found in rock layers dating to the early Jurassic period. The animal was a large predator, several meters long, capable of active hunting. It was not a small scavenger surviving at the edge of habitability. It was an apex carnivore occupying the top of its ecosystem. The presence of a predator of this size implies a stable food web. Large carnivores require abundant prey, and prey species require vegetation. Therefore, the land still supported plant communities sufficient to sustain herbivorous dinosaurs. Fossil bones of plant-eating species have also been recovered, including Glacialisaurus, a long-necked herbivore that browsed on high foliage. These animals lived in the same seasonal cycle of extended daylight and prolonged darkness as earlier forest inhabitants. The key question becomes how reptiles, traditionally thought to rely on external heat, survived months without sunlight and freezing temperatures. Evidence suggests dinosaurs were not strictly cold-blooded in the traditional sense. Bone structure analysis shows growth rates faster than those of modern reptiles. Such rapid development indicates higher metabolic activity. Insulating coverings, possibly early feathers in some species, would have retained body heat. Rather than basking constantly, they maintained internal temperature through metabolism. Behavior likely contributed as well. Some dinosaurs may have migrated short distances towards slightly warmer regions during winter, though not across entire continents. Others probably sheltered in forested valleys, protected from wind. Juveniles could have remained in burrows or beneath dense vegetation. Fossilized bone beds containing individuals of multiple ages imply group living, which would assist survival in harsh seasons. Polar winters presented a challenge not only of cold, but of darkness. Without sunlight, plant growth stopped. Herbivores needed stored fat or access to evergreen vegetation. Fossilized wood suggests some Antarctic plants retained leaves year-round, providing limited food even in winter. Dinosaurs feeding on bark, roots, or dormant plant tissues could survive until spring. Trackways preserved in sediment reveal activity patterns. Instead of showing complete disappearance during winter layers, footprints continue through seasonal deposits, indicating animals remained present rather than migrating completely away. The polar environment shaped behavior but did not prevent occupation. Aquatic systems supported additional life. Rivers and lakes remained partly unfrozen beneath surface ice, sustaining fish and smaller organisms. Some dinosaurs may have relied on these resources during lean seasons. The ecosystem was less productive than tropical environments, but stable enough to maintain populations over millions of years. The presence of dinosaurs in Antarctica alters the perception of prehistoric climates. It shows the world during the Jurassic and Cretaceous was warmer overall than today. Polar regions experienced milder temperatures and global greenhouse conditions reduced extremes. Antarctica was cool, but not the barren wasteland it would later become. As Gondwana began slowly separating, the continent's climate was already trending cooler, but life adapted continuously. Dinosaurs evolved alongside these changes, demonstrating flexibility greater than earlier reptiles. Their ability to inhabit polar environments may have contributed to their global success across diverse climates. The Antarctic dinosaur ecosystem represents a midpoint in the continent's history. It was no longer the swamp-dominated Permian forest, yet not the frozen desert of today. It was a temperate polar woodland, inhabited by large animals capable of enduring long winters and exploiting endless summers. For millions of years, herds of herbivores moved among trees while predators followed their paths. Snow may have fallen seasonally, but it melted each year. Rivers continued to flow. The sun vanished for months and returned again, and life adjusted to its rhythm. The bottom of the world was still a functioning habitat, supporting creatures that walked the same ground, now buried beneath kilometers of ice. The polar dinosaur ecosystems of Antarctica were not accidental populations stranded at the edge of survivability. They were specialized communities shaped by the continent's unusual environment. Each seasonal cycle imposed pressures that influenced anatomy, behavior, and reproduction. Over generations, the animals that remained were those capable of functioning within extreme variation rather than constant warmth. The most defining challenge was the absence of sunlight during winter. Unlike modern polar mammals that depend on fur and high metabolic heat, dinosaurs relied on a combination of physiological efficiency and ecological strategy. Bone histology studies reveal dense networks of blood vessels within their bones, indicating rapid growth and sustained metabolism. This suggests they maintained relatively stable body temperatures internally, allowing activity even in cooler conditions. Young dinosaurs faced the greatest risk. Eggs laid shortly before winter would not survive prolonged freezing. So reproduction had to align precisely with seasonal light. Fossil nesting sites from other polar regions suggest breeding occurred during the continuous summer daylight. Eggs hatched while food was abundant, and juveniles grew quickly before darkness returned. Growth rings in fossil bones confirm accelerated development during early life stages. Likely an adaptation ensuring young reached sufficient size to endure winter. Herd behavior may have played a critical role in survival. Trackways preserved in Antarctic sediments show multiple individuals moving together across muddy ground. Group living would help locate food sources and offer protection against predators during low visibility periods. For herbivores, collective movement could expose buried vegetation beneath snow layers, increasing feeding efficiency. Predators adapted to these same cycles. Cryolophosaurus, as a large carnivore, depended on consistent prey availability. It likely hunted more actively during summer months when herbivores ranged widely and daylight never ended. During winter, its activity probably decreased, conserving energy while relying on weakened or slow-moving prey. The seasonal abundance created periods of intense ecological interaction, followed by relative quiet. The forests themselves changed structure compared to earlier periods. Conifers and hardy seed plants replaced many older fern-dominated wetlands. These plants tolerated cooler conditions and shorter growing seasons. Some retained needles year-round, providing limited nutrition even during dark months. Herbivorous dinosaurs capable of processing fibrous material could survive on bark and tough foliage, unavailable to less adaptable animals. Evidence of burrowing species provides further insight. Small vertebrates excavated underground shelters, traces of which remain preserved as filled tunnels in rock layers. These burrows maintained more stable temperatures than the surface, offering refuge during winter storms. While large dinosaurs could not use such shelters, smaller animals and juveniles benefited greatly, supporting a diverse community beyond the dominant species represented by large skeletons. Water systems remained central to survival. Lakes did not freeze solid due to geothermal heat and insulating ice layers above liquid water. Fish and invertebrates lived beneath the surface, forming food sources for semi-aquatic animals. Shorelines hosted seasonal feeding grounds where multiple species converged. Sediment deposits rich in organic material confirm repeated occupation of these zones across years. The Antarctic environment during this era was neither tropical nor truly polar by modern standards. It was a temperate, seasonal woodland with periodic snowfall and long darkness, but lacking permanent ice sheets. Average temperatures likely hovered just above freezing for much of the year. This moderate climate allowed reptiles with elevated metabolism to dominate without competition from cold-adapted mammals which had not yet diversified extensively. As the Jurassic transitioned into the Cretaceous period, continental drift accelerated. Connections between Gondwana fragments narrowed. Antarctica slowly shifted farther south, increasing the severity of seasonal conditions. Winters lengthened slightly, and summers shortened. These changes did not immediately remove dinosaurs, but they placed gradual pressure on populations. Fossil diversity decreases in later Antarctic deposits. Some species disappeared locally while persisting elsewhere. This pattern indicates migration routes were becoming limited as oceans widened between landmasses. Animals could no longer easily move north to escape deteriorating climates. Isolation began shaping evolution more strongly than before. Vegetation mirrored this trend. Plant fossils show increasing dominance of cold-tolerant species and declining variety overall. Growth rings become more pronounced, reflecting sharper seasonal contrasts. The ecosystem still functioned, but resilience was weakening. The margin between survival and collapse narrowed over millions of years. Dinosaurs remained part of Antarctica until near the end of the Cretaceous period. Even as global conditions fluctuated, they endured the continent's slow cooling. Their presence demonstrates that Antarctica's transformation into ice did not begin abruptly after their extinction. Instead, the land supported complex animal communities almost until the age of dinosaurs ended worldwide. When the final Cretaceous extinction occurred, eliminating non-avian dinosaurs everywhere, Antarctica lost its largest terrestrial inhabitants along with the rest of Earth. But the continent itself had already begun shifting toward colder conditions independent of that event. The disappearance of dinosaurs marked the end of one era of life, not the start of the Ice Age. For millions of years afterward, forests still covered the land. The sun still returned after each winter. Yet the environment was gradually approaching a threshold beyond which large animals would never again walk its surface. After the disappearance of the dinosaurs, Antarctica did not immediately become empty. Forests still covered much of the land, and animal life continued in forms that replaced the great reptiles. Mammals and birds spread across the southern continents, occupying ecological roles left vacant after the global extinction. For a time, the continent remained part of a connected world. But beneath the soil, the planet continued its slow rearrangement. The supercontinent Gondwana had already begun to fracture during the age of dinosaurs, and now the separation accelerated. South America pulled westward, Australia shifted north, India raced toward Asia, Antarctica remained at the center of these movements, increasingly isolated as oceans widened around it. At first, The changes affected coastlines more than climate. Shallow inland seas formed along rift valleys, and marine sediments began appearing where forests once grew. Fossil shells found in coastal rock layers show ocean water periodically flooding lowlands. These incursions altered habitats, but did not yet destroy them. The interior still supported trees and freshwater systems. However, the distance between land masses steadily increased. Migration routes that once allowed animals and plants to spread across Gondwana narrowed into thin corridors. Species populations became separated. Isolation encourages evolution, but also reduces resilience. If conditions deteriorate in one region, replacement from neighboring areas becomes impossible. Plant fossils from this time display reduced diversity compared to earlier eras. Some species persisted only in limited zones. Others vanished entirely from Antarctic records while continuing elsewhere. This was not a sudden extinction, but a gradual thinning of ecological variety. The continent was becoming biologically independent. Ocean circulation began changing as well. Water now flowed more freely between the fragments of Gondwana. Instead of large enclosed seas, currents connected wider basins. Warm water from equatorial regions still reached Antarctic shores, but less directly than before. Temperature differences between seasons grew stronger. Summers remained mild, yet winters cooled further. Sediment evidence reveals the shift clearly. Layers containing remains of warm, adapted plants alternate with layers indicating colder conditions. Growth rings in fossil wood grow narrower, showing shorter productive seasons. Some river deposits contain pebbles scratched by ice during winter transport, suggesting seasonal freezing more severe than before. Permanent glaciers had not formed, but freezing was no longer temporary everywhere. Mountain building also contributed to climate change. As plates collided and separated elsewhere on Earth, new mountain ranges rose. Fresh rock exposed to weather reacted with carbon dioxide in rainwater, removing greenhouse gases from the atmosphere. Lower carbon dioxide levels weakened the global greenhouse effect. This cooling trend affected the entire planet, but had amplified consequences near the poles. Animals responded by adapting or disappearing. Fossils of early mammals and birds show species capable of enduring cooler temperatures. Feathers and fur provided insulation absent in earlier reptilian ecosystems. Yet even these adaptations had limits. The continent's winters were becoming increasingly harsh. Geological records from Antarctica show increasing amounts of coarse sediment carried by stronger winds. Drier conditions developed inland as temperatures dropped. Forests retreated toward coastal regions where the ocean moderated climate. The center of the continent began losing large vegetation cover, replaced by more sparse plant communities. Meanwhile, the sea floor between Antarctica and other continents continued spreading. The gap between Antarctica and Australia widened significantly during the early Cenozoic era. A shallow marine connection remained, but currents intensified through it. The same occurred between Antarctica and South America, where a narrowing land bridge still blocked full circulation but weakened with time. These changes prepared the stage for a major climatic shift. While Antarctica still supported forests and animals, it was approaching a geographic configuration that would alter global heat distribution. The continent's future climate depended less on its latitude and more on the oceans surrounding it. For millions of years, Antarctica balanced between temperate and cold conditions. Each century brought slightly cooler winters and slightly shorter summers. No single generation of organisms experienced dramatic transformation, yet over geological time the trend was undeniable. The world beneath their feet was drifting into isolation, and with isolation came vulnerability. The continent had not yet frozen, but warmth no longer held permanent claim. As the continents continued separating, Antarctica's position alone did not determine its fate. The critical factor was water. Oceans transport heat more efficiently than air, and the routes those waters follow decide whether a region remains temperate or becomes frozen. For millions of years, partial barriers around Antarctica allowed warmer currents to reach its coasts. Once those barriers weakened, the balance changed. The land bridge between Antarctica and Australia was among the first to open significantly. Shallow seas widened into deeper channels, permitting stronger currents to pass. Warm water from lower latitudes still entered the region, but now it mixed with colder southern water more rapidly. This reduced the heat reaching inland areas. Coastal forests began shrinking, replaced by vegetation adapted to cooler climates. The connection with South America persisted longer. A narrow stretch of land restricted full circulation between the Pacific and Atlantic Oceans at high southern latitudes. This barrier slowed the formation of a continuous current around Antarctica. As long as it existed, some warmth remained trapped near the continent, but tectonic forces gradually stretched and thinned this region. Geological evidence from marine sediments shows a steady drop in sea surface temperatures near Antarctica during this period. Microfossils of plankton species sensitive to temperature disappear in sequence, replaced by cold-tolerant forms. These tiny organisms act as reliable climate indicators, revealing changes far more precisely than larger fossils. On land, plant communities underwent major restructuring. Deciduous species that shed leaves each winter became dominant over evergreen types in some regions, an adaptation to prolonged cold seasons. Later, even these struggled to survive in the interior. Pollen records extracted from rock layers show declining variety and abundance, indicating shrinking forests and expanding open ground. Snow began persisting across entire winters in certain elevations. Unlike earlier eras where melting erased accumulation each summer, some patches remained year-round in shaded valleys and mountains. These areas marked the first steps toward glaciation. Ice does not need extreme cold to begin forming, only a situation where snowfall exceeds melting over time. Animals faced increasing pressure. Migration options were limited as oceans widened. Fossil evidence suggests certain mammals disappeared locally while continuing in Australia and South America, demonstrating geographic isolation. Birds capable of flight adapted more successfully, but even they gradually shifted ranges northward. Antarctica was losing inhabitants not through sudden catastrophe, but through steady retreat. The atmosphere amplified the process. With decreasing greenhouse gases, global temperatures fell incrementally. Polar regions cooled fastest because they received the least solar energy to begin with. Seasonal ice cover in nearby seas lasted longer each year, reflecting sunlight and reinforcing cooling. This feedback loop strengthened with every passing millennium. Eventually, the remaining land bridge between Antarctica and South America fractured completely. Seawater flooded through, connecting the Pacific and Atlantic at southern latitudes. This event allowed an uninterrupted ocean current to form around the continent. Unlike previous currents that bent toward land, this one circled endlessly without obstruction. The newly formed circulation isolated Antarctica thermally. Warm equatorial waters could no longer flow directly toward it. Instead, cold water spun continuously around the continent, acting as a barrier. Temperatures dropped more sharply than at any previous time in its history. Glaciers expanded from mountain valleys outward. Snow accumulated over wide areas, compressing into ice. Once formed, ice reflected solar radiation back into space, reducing surface heating. Cooling intensified further. Forests that had survived gradual change for millions of years collapsed within a comparatively short geological span. River systems altered as well. Flow became seasonal and then intermittent. Some channels filled with sediment as vegetation vanished and erosion increased. Lakes froze longer each year until many became permanent ice basins. Only coastal margins retained brief thaw periods during summer. The transformation did not produce immediate total coverage by ice sheets. Instead, advancing glaciers carved valleys and transported rock debris toward the sea. Dropstones in marine sediments increased dramatically, evidence of icebergs breaking off and melting offshore. Antarctica was entering a new phase where ice dominated landscape formation. By the end of this period, the continent had crossed a threshold. It was no longer a cold, forested land, but an emerging ice-covered terrain. The change was driven not by a single event, but by the completion of geographic isolation and the creation of a powerful surrounding current. Antarctica had drifted far enough away from warmth that it could not easily return. The final cooling of Antarctica was not caused by snowfall or long winters alone. It was caused by water in motion. When the last land barriers broke apart, the ocean around the southern continent reorganized itself into a pattern unlike any other on Earth. A continuous ring of moving water formed, circling Antarctica from west to east without interruption. This flow became the Antarctic Circumpolar Current. Unlike regional currents that transport warmth north or south, this one isolated a continent. Warm equatorial waters approaching the south were deflected away before they could reach the land. The current acted as a thermal wall, separating Antarctica from global heat exchange. From that moment forward, the continent could no longer rely on ocean circulation to moderate its temperature. Before this shift, even during cooler ages, warm currents periodically bathed Antarctic shores. These waters released heat into the atmosphere softening winters and melting snow during summer. Forests survived because the ocean delivered energy stored near the equator. Once the circumpolar current strengthened, that energy never arrived. Sea surface temperatures dropped sharply. Marine sediments record a sudden increase in cold, adapted plankton species and a disappearance of warmer water forms. Oxygen isotope measurements taken from microscopic shells reveal a significant global cooling event centered around the southern pole. Antarctica had crossed into permanent cold conditions. Snow that once melted seasonally now accumulated year after year. Each winter added a thin layer. Over centuries, these layers compressed into dense ice. Glaciers formed not only in mountains, but across plains. As they grew heavier, they began flowing outward under their own weight, grinding the ground beneath them. This grinding reshaped the landscape. Valleys deepened, and bedrock became polished and striated. Rocks trapped in the ice acted as cutting tools, carving grooves into the continent's surface. Sediments carried by glaciers reached the ocean, where they fell to the seabed as icebergs broke apart. The geological record shifted from river-deposited material to glacial debris. The presence of large ice sheets altered atmospheric circulation. Cold air above the continent sank and spread outward across surrounding seas, strengthening winds. Stronger winds reinforced the ocean current, making the thermal barrier even more effective. A feedback loop emerged. Colder conditions strengthened the current, and the stronger current increased cooling. Vegetation retreated rapidly during this phase. Plants that had adapted to cool climates could not survive continuous freezing. Soil froze solid, preventing root growth. Without roots, erosion intensified, exposing bare rock to wind and ice. Remaining pockets of life survived only near the coast for a limited time before disappearing entirely from the land. Freshwater systems collapsed as stable ecosystems. Rivers transformed into seasonal meltwater channels, flowing briefly during short summers. Lakes froze permanently, sealed beneath thick ice layers. Only microorganisms persisted within subglacial water, trapped beneath the ice sheet, isolated from the surface world. Marine life, however, expanded. Nutrients released by glacial erosion enriched surrounding oceans. Cold water holds more dissolved oxygen than warm water, supporting large populations of fish and invertebrates. While land ecosystems died, the seas around Antarctica became highly productive, establishing the foundation of the modern Southern Ocean food web. The growing ice sheet also affected global sea levels. Large volumes of water previously in the ocean became locked on land as ice. Shorelines around the world shifted as sea levels fell. Climate patterns changed far beyond Antarctica, demonstrating that the freezing of a single continent could influence the entire planet. By the time the ice sheet reached major thickness, Antarctica was no longer a place of seasonal hardship, but a permanent frozen system. The continent entered a new climatic state, maintained by ocean isolation and reflective ice surfaces. The forests that had endured for hundreds of millions of years were gone, replaced by an expanding white shield, visible even from space. The freezing of Antarctica marked the birth of the modern polar world. Once the Antarctic circumpolar current strengthened, the transformation of the continent accelerated beyond anything seen in its previous history. Earlier cooling phases had been gradual, allowing ecosystems time to adjust. Now, the environment shifted faster than plants and animals could adapt. Antarctica was no longer merely colder. It had become thermally cut off from the rest of the planet. The new current did more than block warmth. It also stabilized cold. Water circulating continuously around the continent prevented seasonal temperature recovery. Even during summer months, relatively warmer air arriving from lower latitudes could not remain long enough to melt accumulating ice. The ocean itself maintained low temperatures, ensuring the surrounding atmosphere stayed frigid. Glaciers began merging into larger systems. Mountain ice fields expanded downhill until they connected with neighboring glaciers. Over time, these combined masses formed an ice sheet covering wide regions rather than isolated valleys. As thickness increased, pressure at the base caused the ice to deform and flow outward in slow motion. Antarctica's landscape was no longer shaped primarily by rivers and erosion, but by moving ice. Beneath the growing ice sheet, the land surface responded to weight. The crust slowly sank under the enormous mass, a process known as isostatic depression. Some areas dropped hundreds of meters below sea level while still covered by ice. This deepening basin allowed ice to spread even further, anchoring the frozen state more firmly. The continent was physically reshaping under the burden of its own climate. Marine environments around Antarctica changed dramatically. Icebergs calved from advancing glaciers and drifted into surrounding seas, melting and releasing fresh water. This influx altered ocean salinity patterns, reinforcing the density-driven circulation that powered the circumpolar current. Cold, salty water sank and flowed northward along the ocean floor, contributing to global deep-water circulation. These processes influence climates far from the southern pole. Colder, deep water reaching other oceans cooled global temperatures slightly and redistributed nutrients. Marine productivity increased in some regions while declining in others. The freezing of Antarctica therefore became a planetary event rather than a regional one. On land, the last remnants of forests disappeared. Pollen records from sediment layers show an abrupt end to tree populations. After a certain point, only spores from simple moss-like plants appear, followed eventually by almost none at all. Soil formation ceased because weathering slowed under constant ice cover. The biological cycle that had operated for hundreds of millions of years ended within a relatively brief geological interval. Wind patterns strengthened as temperature contrasts sharpened. Dense, cold air descending from the interior flowed toward the coast, generating powerful katabatic winds. These winds scoured exposed surfaces, preventing snow from settling in some areas while piling it deeply in others. Snow dunes formed, compacted, and merged into the expanding ice sheet. Even the coastline evolved. As glaciers reached the ocean, they extended outward over water, forming floating ice shelves. These shelves acted as buttresses, slowing inland ice flow, but also storing enormous volumes of frozen water. When pieces broke off, they created massive icebergs that traveled far into surrounding seas before melting. The continent now possessed characteristics recognizable today: permanent ice cover, minimal liquid water at the surface, and near total absence of terrestrial life defined the environment. Yet, beneath the ice, the land retained the shapes carved by earlier rivers and valleys. Ancient mountain ranges and basins survived, sealed away in darkness. Importantly, the freezing of Antarctica also contributed to the development of ice ages in the Northern Hemisphere millions of years later. By locking away vast amounts of water and lowering global temperatures, the southern ice sheet set conditions that allowed northern glaciers to eventually form. The planet entered a new climatic era, where polar ice became a central regulator of environmental stability. Antarctica had transitioned from participant in global ecosystems to controller of global climate. Its isolation was complete, maintained by ocean circulation and reinforced by feedback loops of ice and atmosphere. No longer changing with seasons, it settled into a long-lasting, frozen equilibrium. The continent had not simply become cold, it had become the engine of cold itself. Even as the ice expanded across Antarctica, life did not vanish instantly. The transformation from forest to frozen desert took millions of years, and during that long decline, a shrinking community of organisms clung to survival. They were not large animals like those of earlier eras. They were smaller, quieter forms of life, adapted to narrow ecological margins. At first, patches of vegetation survived near coastal regions, where ocean water moderated temperature. Summers there still produced brief thaws. Mosses, small shrubs, and hardy flowering plants replaced the tall trees that once covered the continent. Fossil pollen preserved in younger sediments shows a gradual reduction in size and complexity of plant species. Each layer upward represents a simpler ecosystem than the one before it. Insects remained among the last active land animals. Their small bodies required fewer resources, and many species could survive extreme cold by entering dormant states. Eggs and larvae endured freezing conditions within soil and under snow cover. During short summers they emerged, reproduced quickly, and returned to dormancy. These rapid life cycles allowed them to persist even as the environment deteriorated. Freshwater systems supported additional survivors. Shallow ponds formed from seasonal meltwater during the warmest months. Microorganisms flourished briefly, feeding small invertebrates. Sediments deposited in these ponds contain microscopic shells and organic material, evidence of repeated seasonal productivity. However, each cycle grew shorter. Thaw periods lasted weeks instead of months, then days instead of weeks. Birds likely nested along ice-free coasts during this transitional time. Unlike land-bound animals, they could migrate north during winter darkness and return when sunlight returned. Their presence would have been temporary but regular, representing one of the final links between Antarctica and broader ecosystems. As ice advanced to the shoreline, even these nesting grounds diminished. Marine life increasingly dominated the region. Nutrients carried by glaciers into surrounding seas encouraged plankton growth. Fish, mollusks, and marine reptiles in earlier times had already adapted to cooler waters, and later marine mammals would thrive in the cold environment. While the continent itself lost inhabitants, the ocean beside it became a refuge. The interior, however, became hostile to almost all complex organisms. Permanent ice-covered valleys and plains, eliminating soil exposure. Without soil, plants could not root. Without plants, herbivores vanished. Predators soon followed. The land transitioned from seasonal hardship to biological emptiness. Yet, beneath the ice, pockets of water persisted. Geothermal heat from Earth's interior prevented complete freezing at certain depths. Subglacial lakes formed, sealed beneath kilometers of ice and isolated from the atmosphere. These environments remained liquid for hundreds of thousands, even millions of years. Within them lived microbial communities adapted to darkness, pressure, and cold. These microorganisms represent descendants of ancient ecosystems, survivors of a vanished world. Chemical analysis of subglacial water reveals metabolic processes independent of sunlight, using minerals from bedrock as energy sources. Life, though reduced to microscopic scale, never fully disappeared from Antarctica. The coastline marked the final battleground between warmth and cold. Glaciers reaching the sea created narrow ice-free strips where meltwater occasionally flowed. In these areas, lichens and simple plants may have persisted the longest. Over time, advancing ice covered even these refuges, and the last continuous terrestrial ecosystems ended. By this stage, Antarctica no longer functioned as a continent supporting resident animal populations. Instead, it became a seasonal destination for marine birds and mammals that relied on surrounding oceans but not on the land itself. The role of the continent shifted from habitat to environmental influence. The last creatures of Antarctica were not destroyed by a single catastrophe. They were gradually outpaced by a climate change too steady to resist and too powerful to escape. Each generation lived slightly farther north than the previous, until only microscopic life remained beneath the ice. The living continent had become a frozen archive. As the ice sheet thickened across Antarctica, survival on land shifted from adaptation to endurance and finally to absence. The remaining ecosystems did not collapse all at once. Instead, they fragmented into isolated refuges separated by expanding fields of permanent ice. Each refuge functioned like a shrinking island surrounded by a frozen sea. Coastal margins became the final strongholds of terrestrial life. Here, ocean influence moderated temperature slightly, and seasonal melting exposed rock and soil for brief intervals. Hardy plants such as mosses and early lichens dominated these regions. They required little warmth and could photosynthesize quickly during limited sunlight. Fossil spores preserved in late sediment layers indicate these simple plants persisted long after trees disappeared from the continent. Small invertebrates depended on them. Mites, primitive insects, and microscopic worms lived within thin soil layers formed by decaying organic matter. Their life cycles were extremely short. They reproduced during short summer thaws and entered suspended states when temperatures dropped again. Some likely survived freezing entirely, protected by biochemical processes preventing ice crystal damage within cells. Freshwater habitats diminished steadily. Lakes that once thawed each year remained frozen at the surface even during summer. Beneath the ice, liquid water survived only in thin layers heated by sunlight absorption and geothermal warmth. Microbial mats continued growing in these environments, forming layered structures that trapped sediment. These communities were among the last stable ecosystems on the continent's surface. Birds, and possibly early marine mammals, visited seasonally, feeding along the coast where ocean productivity increased due to glacial nutrients. They did not rely on land vegetation, but on marine life thriving in cold water. Their presence marked a transition. Antarctica no longer supported independent terrestrial food webs. It had become an extension of the surrounding ocean ecosystem. The interior grew increasingly silent. Glaciers advanced outward from highlands, merging into a continuous sheet that buried valleys and plains alike. Wind scoured exposed surfaces, removing loose snow and revealing hard blue ice beneath. Without soil exposure, even the simplest plants could not anchor. The remaining refuges vanished one by one. Subglacial environments became the only permanent habitats. Beneath kilometers of ice, pressure and geothermal heat maintained liquid water bodies sealed from the atmosphere. Chemical energy from rock minerals sustained microbial life. These organisms required no sunlight and no connection to surface ecosystems. They represented the final biological continuity between ancient Antarctica and the frozen continent. Geological records show that by this stage, pollen and spore presence in new sediment layers nearly ceased. Wind carried almost no organic material from the continent into surrounding seas. This absence indicates the effective end of land-based vegetation across most of Antarctica. What remained was limited to microscopic colonies hidden beneath ice or temporarily active at the margins. Ocean life flourished in contrast. Cold, nutrient-rich waters supported vast plankton blooms, feeding fish, squid, and eventually seals and whales in later ages. Antarctica's ecological importance shifted entirely offshore. The land no longer hosted ecosystems, but influenced those around it through climate and ocean chemistry. The disappearance of terrestrial organisms was not sudden extinction, but progressive retreat. Each species moved or adapted until no viable habitat remained. The process took millions of years, long enough that no single generation experienced the full change. Yet, in geological perspective, the continent transitioned from forest to sterile ice with remarkable speed. By the end of this transformation, Antarctica existed as a continent almost devoid of visible life. Only wind, ice, and distant ocean sounds defined its environment. Beneath the surface, Microscopic survivors continued ancient metabolic cycles, but the age of forests and animals had fully ended. The last creatures had not fought the cold. They had simply been left behind by a world that moved into ice. Once Antarctica became fully ice-covered, its role in Earth's climate changed permanently. The continent was no longer responding to climate, it was controlling it. A massive sheet of ice, kilometers thick, now reflected sunlight back into space and cooled the atmosphere above it. This cooling spread outward across oceans and influenced global weather systems. Ice differs from land or water in one critical way. It reflects far more solar radiation. Dark soil absorbs heat, warming the air above it. Open ocean stores energy and releases it gradually. But a white, frozen surface returns much of the incoming sunlight to space. With Antarctica covered in ice, the southern hemisphere lost a major source of heat absorption. Temperatures dropped further, reinforcing the frozen state. The Antarctic circumpolar current continued circling the continent, strengthened by colder air above it. Wind patterns intensified because cold air sank from the interior plateau and moved toward the coast. These winds drove ocean circulation, keeping warmer waters away. The system became self-sustaining. Even if external conditions warmed slightly, the combined effect of ice reflection and ocean isolation prevented significant melting. As the ice sheet grew, it trapped enormous volumes of water that had once been part of the global ocean. Sea levels fell worldwide. Coastlines on other continents extended outward, exposing land bridges in some regions and altering habitats far from Antarctica. Climate patterns shifted across the planet as ocean basins changed shape. Sediments deposited in ocean floors record these global consequences. Layers corresponding to Antarctic glaciation show increased dust carried by wind, indicating drier climates elsewhere. Cooling allowed ice sheets eventually to form in the northern hemisphere as well, though millions of years later, Antarctica acted as the first step in a long planetary trend toward periodic ice ages. Within the ice itself, a new kind of record formed. Each year, snowfall added a thin layer compressing older snow beneath. Air trapped between snowflakes became sealed bubbles as pressure increased. These bubbles preserved samples of ancient atmospheres. By drilling deep cores into the ice, scientists would one day read a continuous history of climate extending back hundreds of thousands of years. Chemical signatures in these layers reveal cycles of colder and warmer global periods. Even during warmer intervals, Antarctica remained frozen because the underlying mechanisms maintaining its ice sheet persisted. The continent had crossed a climatic threshold, beyond which complete thaw became extremely unlikely under natural conditions. The thickness of the ice also reshaped the land beneath. Some regions were pushed far below sea level due to the immense weight. Others rose slightly as surrounding crust adjusted. Subglacial mountains and valleys determined the direction of ice flow, channeling glaciers toward the coast where they formed massive ice shelves extending over the ocean. These shelves periodically fractured, releasing enormous icebergs. When they melted, they distributed fresh water across the seas, influencing salinity and ocean circulation far from the pole. Thus, Antarctica affected climates not only through air temperature, but through ocean chemistry. Despite extreme cold at the surface, the base of the ice sheet in certain areas remained at the pressure melting point due to geothermal heat. Liquid water flowed slowly beneath the ice, lubricating its movement toward the sea. This hidden hydrological system continues shaping the continent today, invisible from above but essential to ice stability. Subglacial lakes provided additional discoveries. Radar surveys detected liquid water bodies hidden under kilometers of ice, isolated for immense periods. When samples from these lakes were studied, they contained microorganisms surviving without sunlight. Some used chemical reactions involving minerals from bedrock as energy sources. These organisms represent direct descendants of ancient ecosystems, maintaining biological continuity since before full glaciation. Satellite measurements allowed scientists to map buried mountains, valleys, and river channels beneath the ice. Entire drainage systems exist there, preserved exactly as they were when water last flowed freely across the land. These structures match patterns seen in temperate regions, confirming that Antarctica once experienced rainfall, erosion, and vegetation cover. Perhaps the most striking evidence came from preserved wood. Fossilized tree trunks discovered along coastal exposures still contained growth rings showing seasonal variation in light. The spacing of rings indicates long summers and dark winters consistent with polar forests. These trees grew at latitudes similar to the continent's present position, demonstrating that global climate was once warm enough to support forests even near the pole. Each discovery changed understanding of Earth's climate history. Antarctica became not only a frozen landscape, but an archive recording atmospheric composition, temperature variation, and biological evolution across tens of millions of years. No other place preserves such a continuous environmental record. The ice sheet acts as a protective seal. Without it, erosion would have destroyed much of this evidence long ago. Instead, ancient ecosystems remain intact beneath layers of snow and compressed ice. Scientists reading these records can reconstruct past climates and understand how the planet shifts between warm and cold states. Antarctica's surface shows only its present condition, but beneath lies memory. The continent that now appears lifeless contains the preserved remains of forests, animals, and flowing water, waiting to be uncovered piece by piece. As more of Antarctica's buried record was uncovered, the continent's role in Earth's history became clearer. It was not simply a place that froze, it was a place that remembered. Every layer of ice preserved a moment in time, and together those layers formed a continuous environmental archive, stretching farther back than any written history and deeper than most geological exposures elsewhere on the planet. Ice cores provided the most detailed timeline. Each annual snowfall compressed the previous year's layer beneath it, trapping tiny bubbles of air. These bubbles preserved the exact composition of the atmosphere when the snow originally fell. By measuring gases such as carbon dioxide and methane in different layers, scientists reconstructed past climates with remarkable precision. Warmer periods showed higher greenhouse gas concentrations, while colder periods showed lower levels. Antarctica revealed not only its own transformation, but the breathing pattern of the entire planet. Dust trapped in the ice added another dimension. During colder global climates, winds strengthened and carried more particles across continents and oceans. Increased dust layers within Antarctic ice corresponded to glacial periods elsewhere in the world. In warmer ages, the layers thinned. The continent recorded distant droughts, volcanic eruptions, and shifts in vegetation thousands of kilometers away. It functioned as a collector of planetary change. Beneath the ice sheet, sediments told an even older story. Drilling projects reached deposits formed before permanent glaciation. These contained fossil pollen, spores, and organic molecules produced by plants that once grew across Antarctica's surface. Some layers indicated swamp conditions, others river floodplains, and still others temperate woodland soils. By dating these materials, researchers trace the slow cooling of the continent step by step rather than as a single event. Subglacial lakes held living evidence. Microorganisms found within them survive without sunlight, using chemical energy from rocks and dissolved minerals. Their existence demonstrates how life can endure extreme isolation and pressure for immense spans of time. These organisms provide insight into early life on Earth and even the possibility of life in similar environments beyond this planet. Radar mapping revealed entire landscapes preserved intact. Buried mountain ranges, ancient valleys, and winding river channels remain beneath the ice exactly where they formed millions of years ago. In some regions, erosion halted completely once ice sealed the surface, leaving features sharper than many modern terrains exposed to weather. Antarctica protects its past instead of erasing it. Understanding this record changed how scientists interpret climate change. The continent showed that Earth's climate system can shift dramatically when certain thresholds are crossed, particularly when ocean circulation patterns alter. It also showed that once large ice sheets form, they tend to persist because they reinforce the cold conditions that created them. Antarctica became proof that planetary environments operate on long time scales beyond human perception. Today, researchers continue drilling and mapping, reading the continent layer by layer. Each sample refines the story of how a forested land transformed into a frozen desert and how that transformation shaped global climate patterns. The ice does not hide history, it preserves it. Antarctica therefore stands as both relic and record. Its surface represents the present, while its interior contains a memory of warmer worlds, drifting continents, evolving life, and shifting atmosphere. The continent that once supported rivers and forests now serves a different purpose. It holds the history of Earth within its frozen depths, unchanged, while the rest of the world continues to move around it. The story of Antarctica does not truly end with ice. The frozen continent appears silent and finished, yet its present state is only another chapter in an ongoing planetary process. Beneath the surface, the same forces that once carried forests across the pole continue operating. Heat moves through the mantle, continents shift, oceans circulate, and atmosphere changes composition. The difference is not that change has stopped, but that it has slowed beyond the scale of human experience. Antarctica today holds more than frozen water. It holds time compressed into matter. Every meter of ice represents centuries of snowfall. Every kilometer represents ages of climate. The deeper one looks, the farther back the world becomes. Near the surface are recent centuries, recognizable to modern history. Deeper lie colder ages, when glaciers expanded across northern continents. Deeper still exist layers formed before human existence, when the climate oscillated through patterns driven by orbital cycles of the planet. Yet even deeper than those lies the memory of warmth. In some regions, the ice rests directly upon ancient soil that has not seen sunlight for tens of millions of years. That soil once supported roots, insects, and flowing water. It has not eroded because it has not been exposed. It is protected not by distance, but by pressure. The ice sheet sealed the land in a form of preservation no other environment provides. Deserts erase, oceans dissolve, forests decay, but ice remembers. This preservation allows modern science to reconstruct worlds that no living organism has witnessed. By combining chemical traces, fossil fragments, and geological structure, a continuous narrative emerges. The forests were real, the rivers were real, the animals adapted to polar darkness were real. Antarctica was not always an extreme environment, but a dynamic ecosystem that responded to global processes. The frozen state is therefore not a natural default. It is the result of specific conditions aligning: the opening of ocean passages, the establishment of a circumpolar current, the reduction of atmospheric greenhouse gases, and the feedback of reflective ice together pushed the continent across a threshold. Once crossed, reversal became difficult. The system stabilized around cold rather than warmth. However, stability in geology does not mean permanence. Plate tectonics continues. The continents are still moving. Over immense spans of future time, Antarctica will not remain where it is now. The same motion that carried it into isolation will eventually carry it elsewhere. Ocean currents will reorganize again, and atmospheric conditions will differ. The frozen continent may one day thaw, not because ice melted seasonally, but because its geographic position changed. The past demonstrates this possibility. The continent has existed as forest, woodland, tundra, and now ice sheet. Each state lasted millions of years, far longer than civilizations endure. The current frozen world feels absolute, only because human observation covers a brief interval. From the perspective of Earth's history, Antarctica is in the middle of a long cycle rather than at its conclusion. Even in its present condition, Antarctica interacts constantly with the rest of the planet. The cold, dense water forming around its margins sinks and spreads across ocean basins, carrying oxygen and nutrients into deep seas. This circulation supports marine life thousands of kilometers away. The continent influences rainfall patterns, storm tracks, and temperature balances across hemispheres. Though it appears isolated, it participates in a global system every moment. The ice also serves as warning and reference. Past layers show how climate responded to changing carbon dioxide levels. They reveal that warming and cooling can occur gradually for long periods and then accelerate once thresholds are reached. The freezing of Antarctica itself illustrates how one change in circulation can transform an entire hemisphere. Standing on the ice today, one stands above buried forests older than most mountain ranges on Earth. The wind that crosses the plateau passes over a landscape shaped by rivers and inhabited by animals long extinct. The continent beneath the ice is not alien terrain, but familiar ground altered by time and temperature. Antarctica remains a place where the past is physically present. It is not only a record of what Earth was, but a reminder of what Earth can become again under different conditions. The frozen silence is not emptiness. It is a pause between climates. Imagine the ice thinning not in centuries, but across geological time, the way it once formed. No sudden collapse, no catastrophic melt, only the gradual retreat of glaciers as conditions shift. The coastline would appear first. Dark rock ridges would rise from beneath white shelves, exposed to sunlight for the first time in millions of years. Meltwater streams would begin as narrow channels tracing paths determined long ago by buried valleys. As the ice withdrew farther inland, landscapes untouched since ancient climates would re-emerge almost exactly as they were left. River basins, carved before glaciation, would fill again with flowing water. Depressions sealed beneath pressure would become lakes. Some would drain through channels still preserved beneath the ice, reconnecting to the ocean along routes established in distant ages. The soil would not immediately support forests. It has remained frozen and compressed too long. Instead, microbial communities already living in subglacial water would colonize exposed ground first. They would form thin biological films across rock surfaces, beginning the slow process of chemical weathering. Minerals broken down by these organisms would produce the earliest true soils of a new Antarctic landscape. Wind would carry spores and seeds from distant continents. In the earliest stages, only simple plants could survive. Mosses and lichens would spread across moist surfaces using meltwater as their source of hydration. Over thousands of years, they would stabilize sediment and build organic layers thick enough for more complex vegetation. The first shrubs would appear along sheltered valleys where water remained available year-round. Climate during such a transformation would not match the ancient greenhouse world exactly. The atmosphere would differ, ocean currents would follow different paths, and continents would occupy new positions. Yet, certain patterns would repeat. Long polar days would again drive intense summer growth. Long winters would force dormancy. Life would adapt to the rhythm rather than resist it, just as it once did. Animals would arrive gradually. Insects would colonize first, carried by air currents or birds. Freshwater organisms would spread through connecting waterways. Over extended time spans, larger animals could migrate if land bridges existed. The reappearance of terrestrial ecosystems would not recreate the ancient past, but would echo its structure, shaped by familiar constraints of light and season. Marine systems would transform as well. Without massive glacial input, the surrounding ocean would warm slightly. Circulation patterns might weaken or shift, redistributing nutrients differently. Some modern cold-adapted species would decline, while others from lower latitudes expanded southward. The Southern Ocean ecosystem, currently defined by ice influence, would evolve into a new state just as it replaced earlier ones. This scenario is not prediction, but possibility demonstrated by history. Antarctica has already transitioned from forest to ice. The reverse requires conditions changing beyond current ranges, but not beyond geological precedent. The continent's past proves that ice is only one phase among many. Yet even without full retreat, the present ice continues to move. Glaciers flow slowly toward the sea, and snowfall replenishes them. The balance between accumulation and loss determines thickness year by year. Measurements show that the system is dynamic rather than static. Antarctica remains active, though its motion is measured in meters per year instead of kilometers per day. The importance of this understanding lies in perspective. The frozen continent appears permanent when viewed over a human lifetime, but its own record shows repeated transformation. Forests endured for hundreds of millions of years, then vanished. Ice endured for tens of millions and still persists. Neither state is eternal. Both belong to cycles driven by planetary mechanisms. If the ice could recede, it would not erase Antarctica's identity, but reveal it again. Beneath the white surface lies a landscape shaped by water and life, waiting not for sudden change, but for time.